All right, good afternoon or good morning, whichever you are.
Wherever you are.
Okay, so I'm going to talk about this, mainly the new photogrammetry operators and the new sensor models in ERDAS IMAGINE 2016. So I'm going to briefly go over. For the new operators, so we have about 19 operators under photogrammetry category. So mainly for photogrammetry, so from basically the point collection, automatic point match, triangulation, auto rectification to DTM extractions. So also you can also do the auto rectification plus some operators you can use to create operations related to the stereo visualization. So I'm not going to go over every one of them here, just simply the list here. So here's down the photogrammetry category, you see all of this APM, associated elevation, automatic point match, compute, the geometry related to computer transformation. Okay, for new sensor models, so we have added six new models in 2016. So for orbital push broom, we have added Goktek 1, Casio set 1 and 2, Spot 7. For rational functions, we have added the Casio set 1 and Spot 7. So if you look at this model setup, so you can see from orbital push broom, you have seen these new ones. Same thing for the rational functions. Here's just one screen capture for one example. So how can you use photogrammetry operators to run photogrammetry workflows? So in this case, this example, so you can do the data triangulation, then you can run also ETM extraction. Okay, so now I'm going to do some kind of live demo. So first thing, let me show. Okay, all right. So first thing, okay, I just want to quickly show these new sense models. Okay, if you start from photogrammetry project, let's give. So when you create the new project, so you can pick orbital push broom model, then you see all the list, the basically entire list of all the orbital push broom models. There's 4 new ones are listed here. So same thing for the rational function, so you will see the new listing. Okay, in this workflow, okay, I'm going to try to use Casio set 2. The reason I'm going to use this one as an example because Casio set 2 has multiple bands, but each band is kind of independent. So there's one user asked how to make a kind of like a layer stack from multiple bands after, okay, because at the beginning, if you look at the layer stack, the results actually, they don't line up. So if we open this kind of data, we pick Casio set 2. If we basically stack them together, okay, so you see this image, basically they don't line up. So it's clearly it's misaligned. So look at the features. So they have that kind of like a shift. So each band is geometrically, although they are close, but it's not close enough. So when you display on top of each other, they just, okay, it's not aligned. So we can use this new sensor model to actually, eventually you can also rectify, then put them stack together as a layer stack, then you will see they line up properly. Okay, so okay, we can add those. Since each band has its own geometry, so we have to add them separately. So we can add all the bands. Each of them will be treated as the individual raster. If you look at the cell array, so each of them is listed here. So then, actually, we can go into, we can measure some control points. Using stereo point measurement tool. The reason, okay, in this case you have 5 bands. They're almost basically it's from a similar from the same location, almost. So it's you have more than 2. It's better to use the stereo point measurement tool since you can display all of them at the same time. So we already digitized some points, so we can load them to just simply show the example. We have some project already have some points there. So let's take a look. Now we can load. So basically display will show all the images for that particular control point. So in this case, so you can go through basically if they are same. If not same, so you can edit them, you can add new points, so you can digitize, you can do all kind of things in this window. So you can basically digitize with as many as the memory allows you to do. Okay, so at this point, so you can, for example, you can run triangulation since we already have a few control points and a few checkpoints. So in this case, you can see it's pretty decent results. In image space, it's about, for checkpoints are about 1 pixel, for the control points about half pixel. So also in ground space is also in the similar fashion. This is in meters. The pixel size of this data is about kind of 10 meters. So it's about half pixel. So if you can accept the results. Okay, let's get out of here. So once we're done and accept the triangulation results, then you can do also resampling for all of them. Since you want to, if you want to stack them, certainly you'd like to rectify all of them, then using layer stack operator, or just the regular Imagine application to do the stacking. So we can quickly, since we don't recommend use mosaic because they basically cover the same area. So there's no point to mosaic them. They are not from, the overlap almost 100, it's basically 100%. Highlight all of them and then click also resampling. All of them will be added. So that's simpler. Okay, I think in this case we just do quick example. So let's just run, or you can batch it. In batch you can run, you can use multiple CPUs, or you can handle to use multiple machines to run accelerated resampling process. This should be very quick because we use a very low resolution. So, okay, once you run this process for all 5 bands, then you can stack them together. Then you display again, you will see basically its images are multispectral images are formed properly, so you can use them. Okay, we can't display that image here. So, okay, this is also rectified image. Okay. Also, okay, for the operators, right now the primary, the sensor type we support for triangulation using operator is rational functions. So we have a couple of new rational function models added to this release. One of them is CasioSat 1. So here's the category for photogrammetry operators. So you can see basically it's so if you look at the categories, it's basically it's from beginning like this APM automatic point match. So you have then you have all the geometry related operators, compute alpha and transform approximation, then compute the transform. You have data triangulation. You can also, if the model is not a rational function, so you can create that basically from imaging application like imaging photogrammetry or geometrical correction tool to calibrate the image. Then you can load that image into this RPC generator, generate rational function model. So which means almost any model you can eventually use operators to run your photogrammetry process. So as long as you can get into the rational function state. So
other than interactive edit of a checkpoint, and you can pretty much use the modeler to do all the things that...
Pretty much, yeah. As long as the one thing, yeah, if we don't have a rational function model, you just need to have that image calibrated with some model, as long as it's, the model is available to the raster. So then this, you have, it's a lot of, these operators are related to DTM extraction. Also, last row of the operators are related to, image pair for stereo visualization. So it's including its geometry, also how to create this rectified raster for stereo view. Let's take a look at some examples. We can use this approach. We're going to use the CasioSat 1 RPC as the example. So we have, let's see. First thing, you'd like to take a look at, so triangulation. So how do you set up a triangulation? Certainly, you have to take the triangulation operator. So you set up the model type. We have all the rational function models listed here. So you can pick one in this case. So you just pick CasioSat 1. Also, you need to put a list of images into, so you can generate a list using a list operator. Then you put the file input. You can put in this example, we only put 1, 2, so 2 images into the list. So if you have 100 images for the list, certainly you can have 100 imports to that. For control points, right now, currently the control points are basically they are in the JSON file. So you can, in this case, we already created that file. So we have a few control points we can use. Also, you can have the model. Once you do the triangulation, you'd like to create a new rational function model. So we provide this output model file template. So you can put output files into that place. Also the transform, so in like for resampling, we use something called the coordinate operation. So in that case, so we'd like to use, so some cases you want to, you can output that kind of operation that we call the transform file. So also you can have triangulation report. So in this case, the points, the control points, after, especially if the input control point file has type points. So you can basically, okay, after triangulation, you can generate the three-dimensional coordinates for that. So you can have output. So you can, in this case, so you, okay, let's override them. Okay. So we have two images here listed. So it's one which forms a stereo pair. So one is from, okay, it's a Casio set 1 data which has control points. So the two images. For Casio set 1, they use metadata.dim. It's it's a special type of proxy file for the raster. So then we have these control points JSON file. Then output folder, we put in the location, the transform file, and the report. Once you provide this information, so the key certainly you have multiple images and you have control points associated with them. Then you can run the triangulation.
But some images come with the RPP files.
The same, doesn't matter.
Okay.
Yeah, as long as you specify the right sensor type, it will automatically find them. So if you cannot automatically find them, then you have to also add a list of sensor model files into this operation. So which is available if you click this guy. So currently this model file name. So if you look at this one, model file names. So right now we disabled it. So we just don't show it. Since okay, it can automatically pick up from the same folder as your raster. So if you can't, then you need to explicitly specify them.
Sure.
So in this case, okay, the results are created. So if we can, okay, it is in the output underscore try, so we can actually take a look. Hopefully I can go to the place. Okay, so here's the location. If you look at the data, we just generated all of them. So here are the data, the newly triangulated results. So two of them are related to the adjustment. So two of them relate to the transformation. So there's also output the control points, then the report. If you take a look at the output control points, it's formed by image points and the corresponding ground points, and then it's a reference to the image list. So here are two images. Also the sensor type there. Okay. So in terms of, okay, this is all the output rational function. They are in the, we call it, okay, the formats. Their formats are similar to the Iconos model, or they are basically a lot of satellite sensors. They are using very similar kind of text file. So this is the file for same for Iconos RPC model. So simply listed coefficients. The transform is just a kind of a JSON file for our coordinate operation. Okay. In this case, so what you see is, okay, one metadata underscore. So the naming for convention is, okay, you have a root name underscore whatever template you specified. But what about you have multiple images, they use same name? Okay, this is the case. We have all the images, they use metadata.dim as a raster name, raster file name. So we simply put an index, put this kind of like in the order of the file in the project list. So to make a unique name. So first one you use metadata underscore. The second one you have metadata underscore 2. So for each input raster, you are going to have a unique output rational function model associated with it. So this information will be used in subsequent operation, for example, like DTM extraction, like okay, auto resampling. Okay, so let's just, this is just for triangulation. Let's take a quick look with another one. So we have, okay, DTM extraction. Okay, let's show another example of this. The one we saw it on the slide. Okay, here, this one will have basically it's run a process from data triangulation to final, okay, DTM extraction to create a point cloud file. So in this case, we're using 3D-Con SGM. We have two operators. Two operators you can use. Okay, the other one is called surface, generate surface. This is based on the imagine photogrammetry operation, the EAT process. So this one is certainly the 3D-Con SGM it's another application to generate DTM. Okay, in this case, so once you have input image, also control points, then you can do the data triangulation. Once you do the triangulation, then you feed that results into this so-called generate epipolar pair, because 3D-Con SGM requires the input images or image pair already in the epipolar geometry. So if it's not yet in epipolar geometry, you have to resample them and generate those epipolar geometry rasters to feed into the 3D-Con SGM. So in this case, so you can import the epipolar left image, epipolar right image, then feed this into a 3D-Con SGM. In this one, we also have, so you can clip the region. So, okay, you don't want to generate a point cloud for the entire overlap area, then you can supply a shapefile to clip them. Okay, certainly you'd like to provide this output point cloud file name. So in this case, we can quickly run this model. So this model, once again, so you have basically the left image, right image. This is since 3D-Con SGM takes in one pair at a time. So you can have so one pair, certainly two images. You have left image, you have right image. Then you have a adjusted RPC model. Then you have output point cloud file. You have control points. Also, you have this clip region for basically trim the output. Then you have the location for this epipolar image, left and right. Okay, here's the general output folder to form those. So once you click OK, it's going to basically quickly run through the process from data triangulation. If you see the green checkbox, so you will see the process going through from the form image list, then data triangulation, then come down to do the epipolar pair generation. So this is actually, epipolar pair probably is the most time-consuming part, since it's going to also kind of like similar to the also resampling process for left image and the right image. Also, you can use reduced resolution, so it's kind of full scale resampling process for two images. Once this process is done, then you can go into the 3D-Con SGM to generate DTMs. We can look at the folder. Okay, the output folder. So if you look at this, certainly it's so if you look at the data, so you will see this triangulation generate these two adjusted RPC files. Now it's generating the left epipolar image. Okay, while it's doing the job, so we're going to show another example for photogrammetry workflow. In this case, how do you want to generate also photos for a lot of images? Okay, how can you do that? You want to create a model for each image, or how can you do a bunch at the same time? So let's create another example. Okay, in this case, certainly, I also only input 2 images as an example to have a mass production of orthophotos. In this case, since the auto generation part is all the same, so you can create a model for that. We call it submodel, and put that submodel as an iterator. But the inputs are different because for auto resampling, it's most likely the cell size, units, projection, DTM source. Even DTM source you can have different for each input. But then resampling method, all those basically can be the same, except input image is different. Then output also name is different. Then input model is different too. So in that case, so if you look at this example here on screen, so we have 2 input images, then 2 output authors, then 2 input models. Certainly each image you have to have associated transformation, then you can do the auto resampling. This model is 3-dimensional. So you have ground to images, ground is XYZ, to image XY. So so once you form these 3 lists, so 1, 2, 3 lists they put into this iterator. Also you can specify the model name here. In this case, since they are all in the format is similar to Iconos, so we just put the Iconos format there. Although the image itself is a Casio set 1 image, but the model itself we already regenerated and put into the kind of like Iconos format. So if we take a look at this iterator, so what do we do? So inside the iterator, we simply set up also, you see this also rectification operator. So you have input image, then you have resampling method. In this case, you can pick bilinear, cubic, bicubic, or Lagrange, or nearest neighbor. So we simply use, we often use bilinear. Also, you can pick your cell size. You can pick also what's the units for the cell size. There are a lot more actually. If you look at it here, there are. So this is the resampling. For the input raster, certainly, Another thing is, how do I get elevation source? Because when you do auto resampling, you'd like to use the DTM or DEM. So you'd like to associate a DTM source with the sense model. So now we will have one photogrammetry operator called the sense model input. In this case, you can input the sense model name. So previously we just generate from data triangulation. You can generate this sense model. Also, this is sense model name actually. So this is the model file name, actual file name. So we generated from the data triangulation. The final one is the raster file name. This is the output. So this one will be repeated again and again. So we call it iterator. So if you come back to this one, so that iterator is the core of auto resampling. So you can call 100 times, 200 times, whatever, as long as you can be able to form the list for image input, another list for auto name, another list for model name. That's it. So, at the same time, this one is finished. So we can, at this point, the point cloud is generated from a pair of Casio set images. So before we go display, we can actually run this to see if we truly get images. So you have 2, Casio set 1 images, then you have 2 output. So let's say, let's put a different name in case, it's, let's say also left image, also right image. The input model, remember we generated 2 models. So one is adjusted, one is metadata underscore adjusted, another one is called metadata underscore 2 adjusted, since they have same root name. So once you click OK here, it's going to run one at a time. So, when it's running, it will be very quick. we can take a look at the results from that. We can close this guy. We can open the point cloud file we just generated. I think this, okay, after this, Sam is going to show more point cloud related operators, editing, manipulation, all kind of stuff. Okay, here we have, we just generated this, okay. I don't see it. This. Okay, let me not generate a pyramid to see what happens. Okay, so since this input image is multispectral, so you will see the RGB encoding also put on this point cloud file. So you can turn off RGB if you don't like it. You can only see the elevation. So yeah, here's the elevation. It's trimmed, since we provided a shapefile to trim the output. So also you can look at it in 3D. So in case, let's increase the Z scale so we can see a little more. Don't see any difference. Certainly you will see some elevation there, right? So it's, because this is a pretty flat area, so you have some difference. Okay, it's still visible. So this is a point cloud for this new sense model. At the same time, okay, the also resampling is done. Okay, so we can take a quick look at the if you look at off, okay, the output also. See here, we have a lift right to, okay, raster output. Okay, so for this particular, if you would say, previously we said, okay, for CASIO 2 images, we'd like to have a layer stack. So if you have these two images, for example, you can quickly, okay, it's using a layer stack operator to do the stacking to form a multispectral image. So this is a, so you can, the stacking, you can have multiple images as a raster input, then put a layer stack, and then you have an output to a new one. So it's so a lot of kind of workflows, operations can be pretty handy just using operators. So once the model is available, I always save them and use again and again. Well, I think this is it from my side.
And there's some questions.
Any enhancement has been made in the GUI tool and for point cloud?
GUI tool for this release, I think we added the some 3D measurement. Okay. Sam certainly can elaborate more when his presentation is upcoming.
So there is a question here from Mr. Yang to Dr. Yang. How to prepare JSON control points for others? Is there a tool to convert from text to JSON?
Okay, at this point, basically it's with okay. At this point, we don't have a handy tool to generate that kind of JSON, but we can generate examples using the automatic point match. So, for example, okay, then you can modify that file to your like. So, okay, for example, like this. You can put quickly. We can put up. Okay, let's see. I think I have one APM example somewhere. Okay, we have one quick example here. So this is a simple example. It's okay. This one, so you have input 2 images. Okay, you create a list. Then you run, okay, so automatic point match. Automatic point match will generate a JSON file in the perfect control point format. So when you run this file will be created. So we can take a look at where this file is. Then we can, it's under, okay, let's change the location. Let's put under output. So we just say test this, test APM JSON. So if we run this process, so it will quickly, if we, okay, in that case you will see, okay, all of these brackets actually formed with color-coded kind of like its features. So it's very easy to edit. So in this case, so you can also collapse them to see more clearly. So in this, also mainly there are 3 parts in this. So it's one thing you do, you can, okay, yeah, you create the existing one, then modify on top of it. So that's I think right now, since we don't have other easy tools to do, okay, directly, yeah, passing an ASCII file, you generate a JSON. No, we don't have that yet. It's certainly down the road we are going to develop some kind of handy tools to do it. Mm-hmm. So just the main thing, as I said, the 3 main things here is one image list, image point list, ground point list, and the image name list. So plus the projection information. Those things, so once you know those basic pieces, it's just refer existing JSON file, you should be able to create one.